These are notes on writing and balancing chemical equations, which is Chapter 11, Section 1 in your book. So just to recap, and we talked about this a little when we were talking about nuclear reactions, a chemical reaction is a reaction where elements break existing bonds and form new ones, yielding or making new substances. So it's basically a rearrangement of how the elements are bonded. So all of the elements that were there initially are still there, but they're rebonded to make new substances. So, for example, you could have several substances having just hydrogen or oxygen, and so depending on how those elements are bonded, it would determine what substance you have. One of our main goals, overarching goals for this unit on chemical reactions, which is all of Chapter 11, is that by the end you should be able to look at two compounds that are kind of thrown together and decide, first of all, if they will react at all, because not everything reacts, right? Everything is made of chemicals. So if you're looking at, say the chemicals that make up your genes and the chemicals that make up your leg, it's a good thing those don't react because you want to be able to, take the genes off and put on new clothes and still have genes at the end of the day and a leg at the end of the day. We don't want just any chemicals thrown together to spontaneously react. So, as I said, the first goal would be to say, okay, we have these two chemicals. Are they going to react? And then if they are, what are you going to get in the end? So I just want you to kind of keep that in mind in the back of your head that that's where we're going in this unit. But before we can even begin to get there, I want to talk just in general about what a chemical equation looks like and how to what's called balance it. For those of you who took physical science or chem lab methods, this is going to be some review. You should already know a lot of this, and hopefully some of the math will come a lot easier the second time around. So chemical equations. Chemical equations are basically written like this. So NaOH, which is sodium hydroxide, plus HCl, hydrogen chloride or hydrochloric acid. Then an arrow, you don't have to make a nice blocky one, a simple arrow will do. Gives us NaCl, sodium chloride, and H2O, water or dihydrogen monoxide. So the first thing is that this arrow here is called a yield sign. And to yield something means to create it, to make it, to produce it. So what this says is sodium hydroxide and hydrochloric acid yield or make salt and water, salt water. Because the salt would then actually dissolve in the water. So you would get salt water, not salt and water, as it like it wouldn't separate out, I guess is what I'm saying. One thing is, I know sometimes at lower levels, maybe in middle school, you're told that a yield is like an equals. And that's not exactly true, because there are some reactions that where it, equals means it's exactly the same on both sides. And in this case, it's not exactly the same. You have NaOH and HCl, so what's actually a strong acid and a strong base, producing salt water. Those two things aren't equivalent. They're two different things. The other thing about an equal sign is, an equals, you can go in either direction, right? So you could say, 3 plus 4, which is 7, equals 1 plus 6. It doesn't matter what direction you go. 1 plus 6 also equals 3 plus 4. And while it's true that some chemical reactions are reversible, actually a fair number of chemical reactions are reversible, some are not. And so it's not quite an equal sign. So that's something to keep in mind, and maybe you need to update your thinking if that's how you've been thinking about it. So then we have two categories of materials or substances. We have what are called the reactants, and those are our starting materials. They are the things that react. So these here are our reactants. And then you've got the products. These would be the products. They are the ending materials. They're what the reaction produces. So reactants are the things that react to produce the products, the things you end with. And in a reversible reaction, obviously, those can switch depending on which direction the reaction's going. I don't know if we're going to get far enough this year to start talking about equilibrium and which direction a reaction goes, but just kind of keep that in the back of your head. I know a lot of people will say, well, it's a chemical reaction if it's not reversible and a physical reaction if it is. That is absolutely not true. I'm going to say that again. It is not true that reversible equals physical and non-reversible equals chemical. There are plenty of reversible chemical reactions, and one that a lot of you are familiar with is recharging the battery on your cell phone. That's reversing the chemical reaction that's gone on in the battery to run it down. You're simply reversing that reaction by running an electric current through it. A good example of a non-reversible reaction is a non-reversible physical change is if I rip a piece of paper in half. Certainly I can tape it back together, but that's not the same. I haven't reversed the rip. So it's a good idea to get rid of that way of thinking. So this sort of breaks down what a reaction looks like, or what the equation looks like, into the reactants, the yield sign, and the products. So then we need to talk about this idea called balancing equations. And the purpose of balancing an equation is to account for conservation of mass. Remember, we talked again back when we talked about nuclear reactions that in physical changes and chemical reactions there's conservation of mass, meaning mass can't spontaneously appear. It doesn't just show up out of nowhere, nor can it randomly disappear. Whatever mass you start with, you need to end with. And then, of course, except in nuclear reactions. So again, let's take the examples I gave. The mass of the battery in your cell phone is the same regardless of whether it's used up or run down or fully charged. The mass of your hair is the same whether, I didn't use hair, did I? I used a piece of paper. The mass of I sometimes use cutting your hair. Also not reversible. The mass of a piece of paper torn in two total is the same as the piece of paper before it was torn. So that's conservation of mass, and so you need to account for that. And I sometimes liken balancing equations to a recipe. So you can say, for example, if you're making cookies, you take some flour, you take some butter, you take some eggs, you take some sugar, you take some chocolate chips, and those are the ingredients you need to make cookies. Which is absolutely true, but you don't take the same amount of each of those things. And if you only have a certain amount of sugar, that's going to limit the number of cookies you can make or the batches of cookies you can make. If you only have one egg, that's going to limit the number of cookies you make. So balancing equations is being really specific and saying it's including the quantities. You need 2 eggs, and you need 2 cups of flour, and you need half a cup of chocolate chips, and you need 1.5 cups of sugar. And then that's going to yield 2 dozen cookies. So you know how much is going in and how much is going out. It's not wrong to say you need the butter, the flour, the eggs, the chips, and you get cookies, right? I mean, that's not an incorrect statement, but it's not going to give somebody the specifics on exactly what they need to make their cookies. So let's look at how this looks in the real world. So here's an example. All right, here is water. And water in this case is going through a process called decomposition. It's decomposing into hydrogen gas and oxygen gas. And this happens when you run an electric current through it. So you get H2O yields H2 plus O2. And this is unbalanced. Take a second, maybe pause the video, and see if you can figure out what's wrong with this equation. So as I'm sure some of you saw, here we have H2, and that corresponds to the H2 here. But here we just have one O, and here we have O2. And so something doesn't seem right. And what some people will kind of propose is, okay, let's just add in plus O here. Okay, so we'd have H2O plus O yields H2 plus O2. And they'd say, okay, so that works. Well, unfortunately, it doesn't work. I'm going to get rid of that. And the reason it doesn't work is because it changes the reaction. In fact, that's not what actually happens. When you run an electric current through water, you don't also need to add random oxygen. You simply run your electric current through water and you get hydrogen and oxygen. And unbalanced is now like the recipe without the quantities. So again, instead of saying it takes this many eggs and this much flour, you're simply saying you need eggs, you need flour. So this is saying you start with water, run an electric current through it, you get hydrogen and oxygen gas. There's no details. So what we need to do is we need to balance this reaction. Another way is it's almost like, besides being very specific, it's almost like chemistry grammar. So it's making this equation grammatically correct. Our next unit is going to be something called stoichiometry. And it's sort of the numbers and the mathematics behind chemical equations. So it'll be saying things like, okay, in this equation, if you want to produce this much oxygen gas, how much water do you need to start with? And will you have extra hydrogen left over, or will you not have, or running the other way? If you have this much water and you want this much hydrogen gas, how much oxygen gas are you going to get? So that kind of thing. Going back to the recipe analogy, it's like saying, okay, I want to make cookies, but I only have 2 eggs. How many cookies can I make in the end? Or if I have 2 eggs and 3 cups of sugar and a 1/4 cup of chips and 1 cup of sugar, what's going to be kind of my limiting ingredient? So what's going to determine how many I can make in the end? If I have 2 eggs and I have a recipe that calls for 3 eggs, that may be what limits it. But if I only need 2 eggs, but I need a cup of chips and I only have half a cup of chips, that will be what limits it. So it's important to understand how to balance equations so that in our next unit we can then manipulate them and say, okay, we only have this much magnesium. Is that enough to run a reaction? Are we going to have extra left over in the end? How's that going to work out? And so that's sort of the why we're learning how to balance. So when I taught this class to freshmen, I would always have them kind of draw out visuals. And so I'm going to start with that for right now. And then the next equation, I'm going to show you how to do it without visuals. So we're going to make hydrogen yellow dots and oxygen green dots. And those of you who had me freshman year, you may remember that I would do M&Ms. And so we're going to make water here. So let me just copy this, and I'm going to say, let's go paste 1, and we're going to bring this over. Let's go over here and do it here. Paste 2, and bring that over. Then we're going to get an oxygen, and we're going to copy that and paste it. So there's my water, then get 2 more for my oxygen gas. 1, 2. And notice what I'm doing here is that whenever something's a molecule, I have the atoms actually touching because those are actually bonded together. Whereas when they're 2 separate molecules, like the hydrogen and oxygen gas here, those aren't touching. So now, whatever I want to add, I have to add the whole molecule. I can't change the reaction. It's sort of like, let me think of a good example with the recipe. It's sort of like take an egg, for example. I've had recipes that have called for 3 eggs, and I want to cut the recipe in half. Well, for a lot of stuff, you can cut it in half. You know, if I need a cup of flour, I can do half a cup of flour. If I need even like a 1/4 cup of chips, I can do 1/8 of a cup of chips. But if I have something that calls for 3 eggs, I can't do 1 1/2 eggs. I have to sort of figure that out. You know, how am I going to do that? I have to either do 1 egg or 2 eggs, but I can't do 1 1/2 eggs. So here, I notice that I have the same number of hydrogens on either side, but I only have 1 oxygen over here and 1 over here. So I want to add another oxygen over on the reactant side. But I can't just add the oxygen. I have to add a whole water molecule. So going back to that idea, I can't change the reaction. If I want another oxygen, then I need to add an entire other water molecule. So now I have the same number of oxygens on either side, but now my hydrogens are unbalanced. I've got 4 over here and 2 over here. So I can add another hydrogen gas molecule over here. And now I've got the exact same 4 hydrogens here and 4 hydrogens here in the reactants. 2 oxygens in the reactants, 2 oxygens in the products. And a good check is I can actually rearrange these and notice that I have the exact same thing on either side of the equation. I'm going to put these back because this is what the actual equation is. So if I were then writing the balanced equation, I would put in coefficients. So coefficients, remember, are those big numbers that tell me how many of a compound or molecule I have. So I would write it like this. 2 waters yields 2 hydrogen gases plus 1 oxygen gas. And this is now balanced. And this also goes back to why people would say, well, why can't I write H4? This is not H4. This is not 4 hydrogens bonded together. It's 2 hydrogens. This is not 4 hydrogens and 2 oxygens bonded together. It's 2 water molecules. And so that's why it was really important way back when to distinguish between your coefficient here, telling you how many of the whole molecule you have, and the subscript telling you how many of each element you have. So let's take a look at another example. And this example is a lot, well, it's more confusing. It's so C2H6, so dicarbon hexahydride, plus O2 oxygen gas yields H2O, water plus CO2 carbon dioxide. So you could absolutely do this by making a lot of little dots. But right away, I'm looking at it going, wow, 6 hydrogens, you know, in the reactants there. That just seems like I don't feel like making all those dots. You are more than welcome to, especially if this is the first time around you're seeing this, and so you still need kind of dots as a manipulative. But let's say you're ready to move on. This is how I would do it. So I would make kind of a T-chart here. And on one side, I would say R for reactants. On the other side, I would say P for products. And then I would list all of the elements. So I've got some carbon. I've got some hydrogen. And I've got some oxygen. So this isn't going to look great because I'm writing with a mouse. But on my reactant side, I have 2 carbon. So I'm going to do 2 little tick marks. And on my product side, I have 1. On my reactant side, I've got 6 hydrogen. 1, 2, 3, 4, 5, 6. And on my product side, I've got 2. On my reactant side, I have 2 oxygen. And on my product side, I've got 3, because I've got the 1 here and then the 2 there. So everything is unbalanced. So the other way, nothing is balanced. And so I need to figure out what I'm going to start with. Take a second and figure out which one you should not start with. Okay, you shouldn't start, in case you're not sure, with oxygen. And the reason is because you've got 1 oxygen here and 2 there, and who knows where you need to add more. So what I'm going to start with is, I'm going to start with carbon, because I simply need to add 1 more over here. So what I'm going to do is I'm going to put a 2 there. And so that's going to now bump this up to 2 carbons. But now I've also changed my oxygen. I've added 2 more here. So we're going to go 1, 2. So now I'm going to balance my hydrogens. I've got 6 here and 2 there. So I'm going to put a 3 here. Again, I apologize for the bad mouse writing. And so now that's going to give me 3. So I've added 4, but it's going to give me a total of 6 hydrogens over here. 1, 2, 3, 4. That's the 4 I've added, plus the 2 I already had, so 6 and 6. But again, I've now added 3 more oxygens. So I'm going to say 1, 2, 3. So now I've got 8 oxygens over here and only 2 over here. So clearly I need 4 here to get me up to 8. And so that'll add 6 more. So 1, 2, 3, 4, 5, 6. And that's going to give me my 6 oxygens, 6 oxygens, 8 oxygens, 8 oxygens, 6 hydrogens, 6 hydrogens, 2 carbons, 2 carbons. So then I would put in, I don't need a 1 here, but I would squeeze a 4 in here actually. Let's do this neatly. We'll text box it in. So here a 4 would go there, here a 3 would go there, and here a 2 would go there. Sometimes you don't pick the right element to start with, and you kind of have to go back and forth and add more here and then add more there. Sometimes it works out really nicely and you get this. And so then I always like to double check. So I've got 2 carbons here, 2 there, 6 hydrogens here, 6 there, 8 oxygens here. I've got 3 here plus 4. Wait, that's not working out now. Why isn't that working out? Huh. All right, well, let me figure this out. Let's go back to the drawing board. So I think this illustrates why you always want to check your work. So let's see, let's get rid of that. I think I must have added an extra one when I added that, the 3 in there, which is a bummer because that makes it a lot harder to balance. Okay, so now I notice I have 8 oxygen over here, but only 7 over here, right? This is 3 plus 4 is 7, meaning I've got to add another oxygen. So this is where I have to make a decision. I only need to add 1 oxygen. So I'm going to add it over here. So I'm going to cross out the 3 and make it a 4. And so now that's also going to change my hydrogen. So now I've got 8 hydrogen over here. So there's my 8 hydrogen. And now I've got 8 oxygen over here, 4 plus 4. Except that now my hydrogen are unbalanced. So, oh, sorry, I've got 8 oxygen over here. I still have, let's see. So I've got 6 hydrogen here, that's right. And now I've got 8 hydrogen here, we're good. So now I need to add more hydrogen over here. But unfortunately, I can only add in multiples of 6. So I'm going to put a 2 in here. So that's going to give me 2 carbon. 1, 2, or 2 more carbon, so a total of 4. 2 times 2 is 4. And I'm going to have a total of 12 hydrogen over here, or 6 more. So let me add those in. Squeeze them in there. And now everything is oh no, my oxygens are nicely balanced, but everything else is unbalanced. So I'm going to kind of start the process over. Carbons, I need more carbons over here. I should have 4 total. So I'm going to cross out the 2. And while it's annoying that I made that mistake, this is actually now a much more instructive balancing equation one, just to show that sometimes you do just need some persistence. So I'm going to have a 4 here. So let's kind of scribble these out. Those were my mistakes there. We'll get rid of that a little later. So now I have 4 carbons here. But now I've changed the number of oxygen. So now I've got, let's see, 8 oxygen plus 4 oxygen. 4 plus 8 is 12, so I should have 12 total. So let's put that in. So now I've got 12 oxygen. The only thing balanced is my carbon. Now my hydrogen is unbalanced again. Over here I've got 12. Over here I only have 8. So I need 12 total. So I would need a 6 here. So let's cross that out and put in a 6. Pencil is the key to this. And so now I've got my 12 hydrogen. So let's put those in. And now I've got 6 oxygen plus 8 oxygen is 14 oxygen. So now my carbons are balanced, my hydrogens are balanced, but my oxygens aren't. I've got, let's see, 5, 6, 7, 8 on my reactant side, whereas I've got 14 over here. So I need 14 on my reactant side, but that's actually pretty easily done. So, because I know 7 times 2 is 14, so I can put in 7 there. And then I can say, okay, that's now 14. So now I've got 14 there. And so now I can double check. Now this time I'm going to double check before I go and put it in with little text characters. So if I've got 2 carbons, I've got 4 here and 4 there, so that's good. I would have 12 hydrogens and 12 hydrogens, so that's good. I've got 14 oxygens, and I've got 6 plus 8, which is 14, so that's good. So now let me balance it for real. And so here I would say, whoops, I've got 2 carbon dicarbon hexahydride, or ethane is the other way you would say that. I've got 7 oxygen gas. I've got 6 water molecules, and I've got 4 carbon dioxide. So that one's obviously a lot harder than the example above. It really depends on the equation. Some of them are going to be easy, some are going to be hard, but if you notice, it's just following a pattern and going back and forth from reactants to products, comparing element to element. So the goal of a balanced equation is you want to make sure that the number of a particular element in the reactants is the same number of that element in the products. You may end up with a completely different number of molecules. So if you notice here in the reactants, you have 2 ethane and 7 oxygen gas for a total of 9. Really, when we get to stoichiometry, we're going to say this is 9 moles. You can say 9 molecules if you want, although at this point, hopefully you're starting to recognize these are also molar ratios. So here you have 9 moles, whereas over here you have 10 moles. So the number of moles doesn't stay the same. The number of compounds doesn't necessarily stay the same, but the number of atoms of each element should be the same, because that's what's going to drive the mass. The mass is simply 4 carbons in the reactants, well, and the products is 4 carbons, 12 hydrogens, 14 oxygens, regardless of how those are distributed. Please take a look at 11.1 in your book, and feel free to put any questions on the YouTube comments or ask in class tomorrow. Have a good night.